Namaskar, Adab, Shat Sri Akal. Welcome to the course in group theory. This is live class 12 part 2. Yes, in the part 1 we have discussed about permutation groups and their notations. With the help of questions we have tried to understand the concepts in a very beautiful manner. I would like to say this channel is dedicated to provide a free, complete course in for CSIR NET, IIT exam and GATE, and we had already completed a real analysis and we are on the way to complete algebra for this session. Yes, you all are welcome over here. I would also like to say that this evening what are the things we are going to discuss. Certainly we will try to understand the cycle notation, their order, I mean to say the order of a permutation group. We will also discuss the odd permutation, even permutation, how can we represent a cycle notation in terms of different product of transpositions. Okay, all these things are going to be discussed in a very beautiful manner. We will also try to understand what are permutation groups, I mean to say what are even permutation group, odd permutation group, and how we used to find the order. Okay, and yes, all these things in a proper way. The number of elements, everything will be discussed in a very beautiful manner. So let's go to start this session. So first of all I would like to start this session with a question that has been asked, that has been given in the last class as a HW, as a homework question. So certainly you can see a question is over here. Two permutations are given in front of you. You can see a sigma which is written as this 2341756, and tau which is 23516 and 47, and then you have to say about the product of this. Okay, so I think if anybody is there then certainly they should try, otherwise I am just going to give the answer of this question. I think some people may be over there and more than one options are correct. Nitu, you are welcome. So first of all we will try to write this sigma into two row representation, because after writing the permutation in two row representation certainly it becomes easier to get the product for sure. So first of all, what is our sigma? We can easily see the elements from sigma is from 1, 2, 3, 4, 5, 6 and 7, and now we are going to follow this sigma. 2 is going to 3, you can see. So 2 is going to 3 and 3 is going to 2, because here you can see that this cycle notation is closed at 2 and 3. So what does it mean? It means 2 is going to 3 and 3 is going to 2. Again you can see 4, 1, 7. What does it mean? 4 is going to 1, 1 is going to 7 and 7 is going to 4. This is what the meaning of this cycle, this second cycle 4, 1, 7. What about 5, 6? 5, 6 means 5 is going to 6 and 6 is going to 5. So this is how we can write our sigma permutation. Now we are given a tau permutation over here. So once again we will write all the elements at first: 1, 2, 3, 4, 5, 6, 7, and here you can see 2 is going to 3, 3 is going to 5. So 2 is going to 3, 3 is going to 5 and 5 is going to 2 again. Okay, how we used to see? 2 is going to 3, 3 is going to 5 and 5 is going to 2 again, and because here at 2 and 5 you can see the things are going to be closed. So yes, this is what the meaning of this cycle. Now 1 is going to 6, isn't it, and 6 is going to 1. This is how the cycle is. So 1 is going to 6 and 6 is going to 1. All right, now you can see the cycles in the form of 4 and 7. So single 4 is written, it means 4 is going to itself and 7 is going to itself. So this is how we have written this sigma and tau. Now it's the time to write the product, and certainly we will not hesitate to write the product. First of all, we used to write the elements 1, 2, 3, 4, 5, 6 and 7. Now tau, sigma tau is the things over there, so we have to find the product. So here you can see 7 is going to 7 and 7 is going to where? 4. So in the product you can see 7 will go to 4 finally, because 7 is going to 7 and 7 is going to 4. So finally our 7 will go to 4. Again you can see 6 is going to 1 and 1 is going to 7. So our 6 will go to where? Yes, 7. Now 5 is going to 2 in tau and 2 is going to 3 in sigma. So in sigma tau 5 will go to 3. In tau 4 is going to 4 and in sigma 4 is going to 1. So finally this 4 will go to 1. Again 3 is going to 5 and 5 is going to 6. So finally 3 will go to 6. 2 is going to 3 and 3 is going to 2. So finally 2 will go where? Certainly at 2. And 1 is going to 6 and 6 is going to 5. So finally 1 will go at 5. So this is how this product has been written. Okay, the product of sigma and tau. First of all, we have written sigma notation in terms of 2-row representation of a permutation. Thereafter, we have written this tau in terms of 2-row representation, and thereafter the product is here in front of you. You can easily see that this 7 was going to 7 and this 7 was going to 4. So finally this 7 will go to 4. So 7, 4 has been written. So in this way we have multiplied these two. And now it's a time to write this sigma tau in terms of what? A cycle. So how would you like to write it? 1 is going to 5. You can see 1 is going to 5. And thereafter 5 is going to 3, 1 is going to 5, 5 is going to 3 and 3 is going to 6. So we have to write 6 over here. 6 is going to 7. So we have to write 7 over here, and 7 is going to 4. So we have to write 4 over here. 4 is going to 1. So now we have started with 1 and finally we reached that 1. So we must have to close the things. And here 2 is going to 2 only, so we can just write 2 over here. And even you are not going to write 2, however it's fine. So that's why you can say that your answer will be what? This sigma tau, and sigma tau is this 1 5 3 6 7 4 with 2 is also okay. Otherwise 1 5 3 6 7 4 is also okay. So that's why the correct answers are B and C options. Okay. So yes, these were the things. Now we are just going to discuss few more things. Okay, a quick questions in front of you, and thereafter certainly we will get the momentum to discuss many interesting things related to permutation groups for sure. So first of all, we can see what every cycle is a product of transpositions. So first of all, people will ask that what is the meaning of a transposition. So I would like to say a cycle of length 2, for example A1 comma A2. This is nothing but a transposition. A cycle of order 2 is called a transposition. So there is a theorem that every cycle is a product of transpositions. For example, if you have this cycle, then certainly you can write it as the product of transpositions. And it is very interesting to see a single cycle can be written as the product of transpositions in multiple ways. Okay, so certainly we are going to discuss all those things. The way of writing a cycle as product of transposition is not unique. It means you may write a particular cycle into more than one way as the product of transposition. Okay, so let's take few examples and thereafter we will come to the question for sure. And I would like to say that if the things are given in front of you like this one, if you are given a cycle 2 3 1 4 5, okay, 2 3 1 4 5, this is a cycle and you have to write it as a product of transposition. So certainly you will write 2 3 3 1 1 4 and 4 5. And you can also write in this way. You can just take this first and last one 2 5 and 2 with 4 and 2 with 1 and certainly this 2 with 3. So this is also transposition, product of transposition. So certainly we can write this particular cycle as the product of transposition in this way and in this way also. And not only these two ways, but more ways are over here. You can write it as 2 5, 2 4, 2 1, 2 3, 3 4, 3 4. Because you can see 3 4 into 3 4 will be E, because you can easily write the product. Okay, for example, some people will ask that why are you writing a particular cycle in different way of product of transposition, and how it is well defined. I mean to say how it is compatible to write the things like this. Then in that case I would like to say, if 1 2 3 this is the permutation, then this can be written as 1 3 and thereafter 1 2. Okay, and if you want to verify it, then you can do what? If you have 1 2 3 and certainly this 1 3 means what? 1 is going to 3, 3 is going to 1 and 2 is constant. And once again this is your 1 2. What does it means? If you have 1 2 3, then 1 is going to 2, 2 is going to 1 and this. And if you will do the product of these two, then you are going to get nothing but this cycle 1 2 3. All right. Yes, you can see the product over here 1 2 3. So 3 is going to 3, 3 is going to 1 and 2 is going to 1, 1 is going to where? 3, and 1 is going to 2 and 2 is going to where? 2. So here you can see, if you will write this as the cycle, then you can see 1 2, 1 is going to 2, 2 is going to 3 and 3 is going to 1. So in cycle notation this is the thing. So you have seen that how this product is nothing but same as this cycle. In the same way, if you will write it as a 2-row representation and if you will do its product, then you are going to get nothing but 1 2 3 in the cycle notation. So if you have a cycle, then you can write that as the product of different transpositions. And here is a very interesting thing I would like to say, that this cycle has 3 elements, and you have, if you want to write it as the product of transposition, then either you have to use 2 transpositions like 1 3 and 1 2, or you have to take the 4 transpositions or 2 transpositions, or you have to take 6 transpositions. So what is a very good observation, that if you have odd number of elements in a cycle, then certainly that cycle can be represented in different way as the product of transpositions, but the number of transposition will be always even if the number of elements in the cycle is odd. Okay. So yes, here is a very interesting note, that in each of the expression in this example, the number of transposition is always even. This is not by chance. We shall prove that if a permutation is expressed as the product of transposition, then the number of transposition is always either always odd or always even. I mean to say, if you have different way to write this cycle 1 2 3, and in one way you are getting even number of transposition, then in any other way you will find even number of transpositions only. Okay, and this makes the things interesting. And writing a permutation in different way, good evening Prashantji. So writing a permutation in different way, okay, gives the concept of odd permutation and even permutation. The counting of transposition decides this, and that's why this is interesting to see. Okay, certainly I am just going to with the statements of the theorem. You have already read during our graduation days, and thereafter we will come to the question for sure. So don't worry that I am not coming with the question. I have a lot of questions and many interesting things to learn, but we cannot skip these important theorems because this is a detailed course on YouTube. So every permutation in Sn can be expressed as the product of transposition. Proof is over here. Sigma, if sigma is a cycle of length k, then order of sigma is equals to k. I mean to say, if you can see k number of elements in a cycle, then the order will be k. You already know all these things. If tau and sigma are disjoint cycles, then order of sigma tau is nothing but the LCM, least common multiple of order of sigma and order of tau. This is also a theorem you must remember. Okay, so yes, after going through all these, let's apply that theorem over here. Here is a question in front of you. You must try your level best to give the order of this permutation in front of you. Okay, I would like to say here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. So certainly this is a permutation over here, and you just need to give the order of this permutation. I hope many people will give the answer within seconds because this is a very basic question over here. Okay, so I just want to see your response for this question, and thereafter we will discuss everything in detail. Some theorems are also this evening. So I'm just waiting for a few response. If anybody is there, then certainly they should try their level best to give the right answer. First of all, what shall we do? We will try to write it as the product of disjoint cycles. How shall you do it? How shall you do it? Because we had already seen the theorem that if sigma 1, sigma 2 up till sigma n are pairwise disjoint cycles, then the order of this product is nothing but the least common multiple of order of sigma 1, order of sigma 2 and order of sigma n. So this time one answer is there on the screen by Shubham, but Shubham, you have tried well, but I am still waiting for the very first correct answer. Take time, give answer. And this time Prashantji is also saying option B is right, but not so. Come on. Try once more because I am still waiting for the very first correct answer. First of all, we must have to write this two-row representation in terms of a cycle. And how shall we do that? You can see 1 is going to 2, 2 is going to 5, and 5 is going to 1. So we must have to close the things. Rajiv ji, you are also welcome. Rajiv ji, you are saying B only, right? But now let's see. 1 is going to 2, 2 is going to 5, 5 is going to 1. So I have written this 1 to 5. 3 is going to 9. And 9 is going to 3. Okay, so we must have to close it. है ना? 3 is going to 9 and 9 is going to 3. It means we have to close this cycle. Now let's write another cycle. 4 is going to 8, 8 is going to 6, and 6 is going to 7. And we have started from 4, and finally what the things we are going to see, that this 7 is going to 4 once again. So we have to close over here. And if you want to find the order, so you can see your sigma has been written as the product of disjoint cycles, sigma row 1, row 2, row 3, isn't it? So if you want to find the order of row, then you will not forget to find the LCM of order of row 1, which is 3, order of row 2, which is 2, order of row 3, which is 4, and the least common multiple is nothing but 12. So 12 is the right answer, isn't it? Least common multiple we need to see. So least common multiple is 12, right? Rajiv ji, are you agree with this? We have to see the LCM, which is 12. Isn't it fine? Not 24, it's 12 only. Yes, Shubhamji. So now I am just going to write few things, and thereafter you will enjoy a lot of questions, basically the questions of partition related to it. Okay, but before coming to all those things, I just want to write a few things and then you have to say the things. Okay, you all know even permutation means what, and thereafter there will be a lot of questions in true false manner. You all know if a permutation will be represented as the product of even number of transpositions, then it is called even permutation. Everybody knows. But now I am just going to ask one thing, that if you are given a transposition, I mean to say, let's take a permutation sigma as 1, 2, 3, then what would you like to say? Is it odd permutation or even permutation? What would you like to say? If you want to say odd, then please write O. If you want to say it's even, then please write E, and thereafter we will have a good discussion on the definition of even permutation, and thereafter we will accelerate ourselves for some really beautiful question. So what do you think? Is it a even permutation or odd permutation? Because the number of transpositions decide whether it is even or odd. Come on, either write O or write E, and thereafter you will get a quick response on that, and we will clear the definition. It will help you to go forward. So please let me know. It's even permutation, which is a very basic question, because this 1, 2, 3 can be written as 1, 2 and 2, 3. Many more ways to write it, but whenever we will write this cycle 1, 2, 3, then certainly we will have even number of transpositions. Okay, and that's why it's a even permutation. Okay, so yes, it was very interesting. Okay, now I am just going to ask some more basic questions, and thereafter we will move ahead. Okay, yes, so even permutation, odd permutation is quite clear. All right, I am just going to ask one very basic but interesting question. If you are given row as 1, 2, then will it be odd or even? What do you think? Is it a odd permutation or even permutation if single thing is there? What do you think? What do you think? Odd or even? It is 1, 2. What do you think? Is it odd or E? Is it odd permutation or even permutation? What do you think? What do you think? Shubhamji is saying yes. I would like to say it's odd. Ashish Tiwari ji, it's odd, because 1 is going to 2 and 2 is coming to 1, and it has only one transposition. It has only one transposition, and if you have only one transposition, then certainly it will be what? Odd. Yes. Now I am just going to ask one more very basic question. Yes, if you are given f is equals to 1, 2, 3, 4 from Sn, and your n is greater than or equal to 4, okay, then what would you like to say? Is it odd or even? Is it odd or even? Permutation, I am just going to ask, is it odd or even permutation? What do you think? Here Sn belongs to Sn, n greater than or equal to 4 means what? You can take 1, 2, 3, 4 from S4, no matter from S5. Okay, if you are taking S5, it means what? 5 is constant. If you are going to take S6, it means 5 and 6 are constant. So that's why these notations are over here. So don't confuse with it. Okay, because one may ask from where this permutation has been taken, 1, 2, 3, 4. then I am saying that it may be taken from S4 or S5 or S6 or S7, no matter. 1 is going to 2, 2 is going to 3, 3 is going to 4, 4 is coming to 1, and rest all are constant if n is greater than 4. And this time Rajiv ji is over there, and certainly it is an odd permutation because it can be written as the product of odd number of transpositions, and it is nothing but 1, 2, 2, 3, 3, 4. Okay, so what can you say? You can write the things like this. So, a product of 3 transpositions, and therefore we will not hesitate to say that this is an odd transposition. One more interesting thing, product of 2 even transposition is once again even, you know already. If you have a even transposition and even permutation and odd permutation, then the product will be odd. If you have odd permutation and odd permutation, then you will get even permutation. So these are the things, and by knowing this, I just want to ask you one thing. There is a theorem, very interesting, but what do you think? I am just going to ask a very good true false question, but I will give you the proof of this, and I would like to say this is a very basic concept, but certainly the questions can be solved with the help of this. So don't take it otherwise. I mean to say, don't take it this is not so important. This is really important. If you are given f is equals to alpha, beta, alpha inverse, beta inverse belongs to Sn, okay, and alpha, beta are the elements from Sn, is always an even permutation. What do you think? This is always an even permutation. What do you think? Certainly it is interesting because I am going to take the cases. Okay, a lot of cases will be there in front of you. Sometimes we will take alpha even, beta odd, beta even, alpha odd, both even, both odd. Okay, so certainly it will clear everything, and if you really give the correct answer of this, then certainly it will help you to understand many things which is really important. So f is what? Alpha beta into alpha inverse beta inverse from Sn is always an even permutation. Do you dare to say this, that always even permutation, no matter alpha is odd, beta is odd? What do you think? Okay, so I am just going to take the cases and then we will come to the conclusion. So we are just taking the case number 1. Yes sir, even. Shubham ji is saying yes, even. So let's take alpha and beta both even. Alpha and beta both even. Then what do you think? If you have f is equals to alpha beta, alpha inverse beta inverse, then you can see what? This is even, this is even, so its product is even. This is so alpha inverse will be also even if alpha is even, beta inverse will be also even if beta is even. So finally even into even will be what? Even. Okay, so you should remember that alpha beta, alpha inverse beta inverse is always even, but the people will say what happens if we will take alpha even but beta is odd. Case 2, if we are taking alpha even, beta is odd, then what the things is going to happen in this case? Alpha beta, alpha inverse, beta inverse. So alpha is even and beta is what? Odd. Alpha inverse will be also even because alpha is even, and beta inverse will be also odd. So finally you can see even into odd is odd and even into odd is odd, but odd is odd, odd into odd is even. So in this case, and similarly for the rest of the cases, you can say what? Certainly what the thing is going to happen, alpha, beta, alpha inverse, beta inverse will be always an even permutation. Okay, so in other case you will certainly verify. You can take the case 3, okay, in which alpha is odd, beta is even, then similarly you can verify it. And in case 4, if both will be odd, then once again odd. But I don't want to waste your time, and that's why I am just going to a very interesting formula. Okay, you must have to be very careful for this question, that number of elements of a particular order in Sn. Okay, this is a very important thing. Number of elements of order D, okay, a particular order in Sn. Okay, number of elements of order D in Sn. What is the formula for this? The formula is factorial n. Okay, I am just going to use some notation, and thereafter we will discuss what the notation says. 1 to the power alpha 1, 2 to the power alpha 2, and by doing so k to the power alpha k, and thereafter what the things are there? Factorial alpha 1, factorial alpha 2, and by doing so factorial alpha k. But now the questions are, what are these things? I am just going to ask, if you have to find the elements of a particular order in Sn. Okay, for example, if you have to find the number of elements of order D in Sn, then what is the formula? Factorial n over 1 to the power alpha 1 into 2 to the power alpha 2 into 3 to the power alpha 3 into k to the power alpha k, and thereafter factorial alpha 1, factorial alpha 2, factorial alpha k. But the people will ask, what is the D over here? Then I would like to say the LCM, least common multiple of 1, 2, 3 up till k is equals to D. And then the people will ask, what are these alphas? Alpha 1, alpha 2, alpha 3. Then I would like to write it very carefully, that alpha I is nothing but number of i's selected, number of i's in selected partition. And now I am coming to the question that may be asked. Okay, first of all, write the formula. I would like to say what is our aim to discuss this formula, that whenever you have to find the elements of a particular order, for example, elements of order D in Sn, then the formula says if Sn is there, then in numerator you have to write factorial n, and thereafter this formula, where this D is nothing but the least common multiple of 1, 2, 3 up till k, and alpha I is nothing but the number of i's selected in the partition. Then the people will ask, what is this number of i's selected in the partition? Then I would like to say, don't worry, I am just going to ask a question, and thereafter everything will be clearer. Okay, yes. So the first question of 3 marks is what? Please read it carefully. The number of elements of order 2 in S5. 2 order के कितने elements होंगे S5 में? You just need to say option A is 2, option B is 5, option C is 25, and option D is 32. So what do you think? Number of elements of order 2 in S5, what do you think? Okay, something were given in the partition. Okay, selected partition. I think formula have been written by you already, and now you are ready to give the answer. Number of elements of order 2 in S5, what do you think? I'm waiting for your response. If anybody is there, then certainly they can say, and we can go ahead. Okay, so the number of elements of order 2. So you will take that partition for which the LCM should be 2. This is the thing, and certainly we will discuss it in a very beautiful manner. I will come to the formula and tell you that what was the meaning of this number of i's in selected partition. We'll discuss everything in detail, and this time one answer is there, Shubham ji is there, but what other people thinks is also interesting. So first of all, in S5, what are the partitions? Okay, so in S5, what are the partitions, so that you can discuss about the elements of order 2. So the partitions will be what? Which kind of partitions will be there? Certainly 2 plus 2 plus 1 wala partition, and another 2 plus 1 plus 1 plus 1. So here you can see 2 plus 2 plus 1, so 5. So you can get the partition in terms of this 2 plus 2 plus 1, and another partition of 5 is 2 plus 1 plus 1 plus 1. Why we are taking only this kind of partition, not other kind of partition? Because we have to find the elements of order 2, and here you can see the LCM of 2, 2, 1 is nothing but 2, and here the LCM of 2, 1, 1 is nothing but 2. That's why we are taking these two partitions. This time Ashish Tiwari ji and Shubham ji is saying the right thing. So congratulations both of you. So only these two kind of partitions should be taken for elements of order 2. Now come to the formula. Here what was the formula? Number of i's selected in the partitions. Okay, and here is factorial n. So how shall you find the number of elements of order 2? So we will find the number of elements of order 2 for both the partition, and thereafter we are going to add. So what is the formula? Factorial n. So it was S5. So first of all, factorial 5 divided by what the things should be there. Things should be there. So you can see how many partitions are there for 2. 1 ka power alpha 1, 2 ka power alpha 2, things like this. So here 2 plus 2 plus 1 is there. So we will certainly like 1 ki power 1 and 2 ki power 2, and thereafter what the things were there? Factorial alpha 1, factorial alpha 2. So factorial alpha 1, so alpha 1 is 1, alpha 2 is 2. So we are just going to write factorial 1 into factorial 2. So this much of elements will be there. So factorial 5 over what the things are there? 4 into 2. So this is what? 5 into 4 into 3 into 2. Isn't it? Yes. So from here what the things are there? These 2 will be cancelled, and 15 elements will be there of order 2 from this partition. What about this one? Okay, once again 5, factorial 5, and thereafter you can see 1 is repeated 3 times. So we will write 1 to the power 3, and 2 is going to be repeated 1 times. So 2 to the power 1, and thereafter this is your alpha 1 at 3, alpha 2 as 1. So factorial 3 into factorial 1. So what the things are there? Certainly you will say 5 into 4 into 3 into 2 into 1 over. This will be what? 5 into 3 into 2. So it will become 3 into 2 cancelled, and 2 2s are 4. So finally it's 10. So 10 elements of order 2 from this partition we can see, and 15 elements of order 2 from this partition we can see. So overall how many number of elements of order 2 in S5 will be there? Undoubtedly 10 plus 15 is equals to 25. So I hope this is clear. I hope this is fine. Now certainly we will come with that, with those questions. Shubham ji, I have noted your comment and certainly will do according to your comment. Sure, but the one thing is what, when I will come live, then certainly you should come, okay, because it gives us motivation. Otherwise I only come when I used to get time. ओके जब समय रहता है सिर्फ तब आते हैं, लेकिन अगर रिस्पॉन्स मिलेगा तो कोशिश होगी कि भाई जैसे भी हो ऑफलाइन से समय निकाल करके निश्चित तौर पे आया जाए. सो आई हैव रिटन योर कमेंट, I mean to say I have noted your comment. So now number of elements of order 3 in S5. What do you think? Order 3 के कितने एलिमेंट्स होंगे? ऑप्शन ए 5, ऑप्शन बी 10, ऑप्शन सी 15, ऑप्शन डी 20. How many elements will be there? Please. Number of elements of order 3 in S5. What do you think? Okay, so you have to take the partition for 3 this time in S5 and thereafter you have to say the things. Okay, you have 5. तो 5 का पार्टीशन जिसमें कि 3 ऑर्डर के एलिमेंट्स प्रोड्यूस हो, तो 5 का पार्टीशन किस तरीके से हो सकता है? दिस टाइम आशीष जी इज वेरी क्विक. सो 5 का पार्टीशन 3 + 1 + 1 के टर्म में हो सकता है, यस और नो? सो टोटल नंबर ऑफ एलिमेंट्स विल बी व्हाट? फैक्टोरियल n. n is 5, 3 is repeated 1 times and 1 is repeated 2 times. So 1 का स्क्वायर, 3 का पावर 1 and 1 का पावर 2 is there. So factorial 2 will be over here and 3 का पावर 1. So factorial 1 will be over here and we will not hesitate to say that this is nothing but 5 into 4 into 3 into 2 into 1, and over here the things are what? 3 into 2. So 3 into 2 will be cancelled out and finally we will have 20 elements only. So this time Ashish Tiwari ji and Shubham ji were absolutely right. So now we are coming to some more questions like this, that if you are going to be asked for number of elements of order 4, number of elements of order 4 in S5. What do you think? How many number of elements will be there? Option A 20, option B 30, option C 25, option D none. What do you think? Come on. Number of elements of order 4 in S5. What do you think? Ashish Tiwari is saying 30. So number of elements of order 4 in S5 is what? Certainly you can say what? 5 S5 we can partition like this, and factorial 5 divided by, what shall we say? 1 is coming 1 times, 4 is coming 1 times, so factorial 1, factorial 1. So this is 5 into factorial 5 into 4 into 3 into 2 and divided by 4 only. So 5 3s are 15, 2s are 30. So 30 will be the right answer. Yes, Rajiv ji, Shubham ji, Ashish ji, absolutely right. Okay. So now I am going to ask something interesting. Okay, different kind of question. What is the maximum order? What is the maximum order of any element? Maximum order of any element in S10. What is the maximum order of any element in S10? What do you think? What do you think? Option A 3, option B 8, option C 20, option D none. Okay, you have to find the maximum order of any element in S10. Namaste Dileshwar ji, you are welcome. Okay, for this question you have to say, Prashant ji, you are also Welcome. So what is the maximum order of any element in S10? This is really interesting. This is really interesting. What do you think? Maximum order of any element in S10. Shubhamji is saying D is the right answer. So can you say what is the number of that order? Can you write the order? Okay. Actually, I would like to say there is a very good partition of 10. Okay. And certainly we have to find the partition so that the LCM will be maximum. Yes, Ashish ji, yes, 5 plus 3 plus 2. And for this combination, for this partition 5, 3, 2, we will have the maximum LCM 5, 3, 10, 5, 3, 2, which is 30. Yes, this is. So now I would like to say in this course I think the next class is on Sunday. At 8:30 p.m. and on Sunday, because certainly we will get time from my offline duty, and certainly I will make a PDF of 10 questions and we will come to play the things. I mean to say, we will come to play the question answer game in a very beautiful manner. Certainly all the questions will be very interesting, and certainly that will be a grand master package, okay, which is there on the thumbnail of my class. Okay, so we'll see you on Sunday at 8:30 p.m. I would like to say thank you very much everyone for coming. I would also like to say that real analysis has been completed on this channel. Certainly you can go and watch. We have a playlist of more than 90 videos, more than 120 hours on this channel only. Okay, so certainly you can watch those classes. And I have also noted the comment of Subhamji, who is saying that come with the questions on uniform convergent and functions of several variables. So certainly we will take a session on it for sure. Okay, so we'll see you in the next class, which is on Sunday at 8:30 p.m. Till then, take care. Bye bye. Good night. And I would also like to say thank you very much all of you for coming. Jai Hind, Jai Bharat, Vande Matram.